So in this video, we are looking at reciprocal models. Now, our reciprocal models describe practical situations using functions in the form y equals k over x, the one we've introduced previously, where k is a number. Now, reciprocal functions are graphed to make a curve in the shape of a hyperbola, which we have been investigating before. Now, when we look at practical situations, the kind of most obvious one that maybe you've definitely seen, but maybe haven't considered as a reciprocal model is, we see in this first example, speed. Now, if you remember the speed formula you learnt back in, say, year 8, maybe even earlier, we said that speed equals distance over time. Now, imagine you live maybe 20 kilometers away from your school, okay? So the distance is a constant, right? So the distance can be any number, but let's look at this case where you live 20 kilometers away from your school. Now, you can see the speed is in the place where y is, and our time is in the place where x is. Now, if you imagine your time taking longer, so say the t increased more and more and more. If it took a lot of time for you to get to school, it means you must have been driving pretty slowly. Your speed must have been low. So as time increases, say your time was a lot more, you must have been going slower. The speed has to compensate for this. Now imagine the time it took you to get to school was really low. You got to school really, really quickly. That means the speed must have been high. There's this opposite relationship happening with speed, our speed, distance, time formula, okay? The distance is constant. The distance actually takes up this value of k, because k can be any number. And we have this idea of opposites happening. As time increases, your speed must have been smaller. If your time's big, your speed's small. If your time is low, your speed must have been pretty high. So just a little kind of intro before we start graphing this relationship here, but just to get you thinking that you've actually kind of already come across this maybe without realizing. But example 1 tells us that the time taken t in hours for a road trip at speed s is given by the reciprocal function t equals 2000 over s. So 2000 here must have been the distance, and this is just a rearranged formula, because remember, we can express time as distance over speed. So we want to first graph up this table of values. Now, thinking our two variables here are time and speed. Generally, time can't be negative and speed can't be negative. So we're only using the first quadrant, like we've done with a lot of our kind of models, our quadratic models, our exponential models, our now reciprocal models. We are just thinking in terms of positives. Now, I've picked these values for my table of values. You can pick any you'd like, but just pause the video, have a go at substituting in, and I will join you at the very end to just put the value straight in. So for the first one, it's going to be 200. Next one, 100. Next one's going to be 50, 40, 33, 25, and then 20. So we're just substituting in using our calculator. So your S values go into here and you're getting a T value out. Now part B is asking us to draw the graph of T equals 2000 over S. Now T is the dependent variable, it's the subject, so that goes on the y-axis. Your S is going to go on the x-axis. So we just want to graph these up. So when the speed is 10, the time is 200. When speed's 20, time is 100. When it's 40, it's 50. When it's 50, times 40. When it's 60, we have 33. And when it's 80, we have 25. And when it's 100, we have 20. So we can see that it's making that general hyperbola shape as we expected. So we are going to just connect up the dots. You may have to turn your page a little bit as you're drawing these. They are a little bit tricky, but here we have our graph. We draw the arrows, and we can see we have our two asymptotes. This is going to get closer and closer and closer to zero. Remember, our time can never be zero. We can't teleport to where we want to go, right? And our speed, basically here, it's gonna approach, but never become zero. So we can take a really, really, really long time, but we're never gonna be like fully stopped and not moving for the entire trip, right? That's why we have these two asymptotes. So here we have our graph of t equals 2000 over s. So part C is asking us, how long did it take at a speed of 70 kilometers per hour? So we're going to use our graph. We want to find 70 here, and we are going to draw up to here. Now this goes slightly above this one because at 80 it's 25. So we draw from the graph along, it's just above this line. So we have 25 over here. So let's say this is approximately 30. So this takes approximately 30 hours. Okay. Now, the last question is a little bit silly. It's saying, why is it impossible to complete the trip in 10 hours? Look, it's definitely possible, but if we substitute this in, I'll tell you why it's a little bit silly. If we put 10 in place of the s, I get t equals 2000 divided by, the speed in 10 hours. So I get that 10 equals to 2000 divided by s. Now, if I rearrange the formula, I multiply the s on this side, 2000, and I get the s equals 2000 over 10. I get a speed of 200 kilometers per hour. Now, in Australia, this is above the speed limit on Australian roads. So legally, we can't complete this trip in 10 hours. Obviously, it's not impossible, but it's essentially illegal, right? So we can say that this is because this would be a speed of 200 kilometers per hour, which is above the speed limit. Okay, so this is how we can just look at our model, look at our reciprocal equation, sketch a graph, use it to predict different values, and once we have this graph, we can make a whole bunch of predictions like we've done in part C. Now, the next part, we have another reciprocal model modeling a practical situation. It's saying the cost per person of sharing a pizza, C, dollars, is dependent on the number of people eating the pizza. And the reciprocal equation, C equals 24 over N, is used to model this situation. Now, here we consider, if we think about it, this is another reciprocal function or reciprocal relationship. Think about there's a cost. So the $24 is the overall cost. The C is just the cost per person. Now, imagine a pizza costs $24. The more people you have, as N gets bigger, the more people you have, the less it's going to cost. It's an opposite relationship again, right? As N gets bigger, C gets smaller. The more people we have, the less it's going to cost per person. The less people we have, the more it's going to cost per person. So we still have this opposite relationship happening here. Now, we have our rule. Now, it's saying to describe the possible values for N. Now, I don't know about you, but I don't want to be sharing one pizza with 30 people or even 20 people, even 15 people. So we have to kind of pick some reasonable values for N. Now, we know N's not going to be negative because we can't have negative people, but we're just going to say N is a positive whole number. Has to be a whole number, right? Because we can't have half a person. And we can say it's likely less than 10. Realistically, it's probably going to be around 8. That's why I've picked it going up to 8, because typically they cut pizzas in 8 slices. So we don't really want less than 1 slice per person. But n must be positive, must be a whole number, and it's likely less than 10, and probably maxes out at about 8. So now that we have that, we want to construct our table of values. So I've picked some different values for n, and I want to substitute into my rule to come up with a cost per person in each of these cases. Now, when there's just one person, it's going to cost $24, 2, 12, 3, 8, 4, 6, 5, 4.8. Let's do that again. When it's 6, there's 4. When there's 7, 3.4. And when there's 8, 3. So these values become points that I substitute into my, plot onto my Cartesian plane and draw up the reciprocal function. Once again, I'm just using the positive quadrant to do this. And let's just go straight in and plot the points. Now, when n equals to 1, c is 24. N equals to 2, it's half. When it's 3, we get 8. When it's 4, we get 6. When it's 5, we get 4.8. When it's 6, we get 4. When it's 7, we get 3.4. And when it's 8, we get 3. Now, we see it forms that shape, the general shape we're after. So now we can just draw this up. So we can connect. And we can continue drawing it in. So we have our graph. This is the graph of C equals to 24 on N. Okay, so next question is saying, what is the cost per person if 6 people are sharing the pizza? We've already done that using our table of values. So we know it's going to cost $4 per person if 6 people are sharing. It's going to be $4 per person. And the next one, this is saying how many people shared a pizza if the cost was $2.40 per person. We're just going to find this algebraically. So here we are saying the cost was $2.40 per person. So 2.4 equals to 24 over n. And we can multiply the n to the other side. So 2.4n equals to 24. And n equals 24 divided by 2.4, which gives us 10. So if it was $2.40 per person, then there must have been 10 people. We are using our reciprocal equation, our rule, substituting in something for C, and then solving for N. That brings us to the end of the video. This is how we can use reciprocal models to model practical situations and then use that graph to answer more questions. But that brings us to the end of the video. Thank you so much for watching, and I'll see you next time.